Welcome to Orbital Dynamics Part 40. This part is based on the book The Mechanical Universe. Some of what I'll say in this part is taken from there verbatim. In fact, I'm going to read to you section 8.1 from the book. Using crude water clocks to time balls rolling down inclined planes, Galileo searched for and found a description of how bodies fall. His law of falling bodies, however, wasn't a fundamental law of nature. Within half a century, it was superseded by a deeper insight into nature, Newton's universal law of gravity. Through the genius of Newton, the force of gravity was revealed as a fundamental force of nature. Inspired by Newton, physicists in the 18th century sought to identify, classify, and mathematically describe the numerous forces observed in nature. Knowledge of these forces provided physics with a certain predictive power because, according to Newton's second law, F equals ma, forces shape the motion of all things. Through painstaking experiments, these physicists reached empirical descriptions of forces in the world about them: tension, spring forces, friction, viscosity, electricity, magnetism, and chemical action. As the number of forces grew, so did the applications in an increasing industrialized world. Yet, a question which confronted these physicists was, are all these forces fundamental, or can they be reduced to more basic forces? Not until late in the 18th century did a second force emerge as fundamental, the electric force. The French engineer Charles-Augustin Coulomb assumed that, analogous to the gravitational force between two masses, the electrical force between two charges is proportional to the product of the charges. Experimentally, he found that the electric force is similar to gravity in another way. The force between two charges decreases as the square of the distance between them. Summarized mathematically, the electric force F between two charges Q1 and Q2, which are separated by a distance r, is known as Coulomb's law, and is written as F equals K sub E times Q1 Q2 over r squared times the unit vector r. Just as G is a gravitational constant for gravity, K sub E is a universal constant for electricity. Magnetism was also identified as a fundamental force of nature. The attraction or repulsion between two magnets could be described by a force between pairs of magnetic poles. The progress of physics appeared to be a triumph of Newtonian mechanics. The forces of nature were successively reduced to attractions and repulsions between particles. The first 40 years of the 19th century, however, saw a growing reaction against such a division of phenomena in favor of some kind of correlation of forces. The turn inward to unification of forces was spearheaded by Ørsted, Ampere, and Faraday. By the middle of the century, they had succeeded in unifying two hitherto disparate forces, electricity and magnetism, into one, electromagnetism. The process was crowned in the theory of James Clerk Maxwell, who expressed the unification by a set of equations which interrelate electric and magnetic phenomena. Soon, tension, spring forces, friction, viscosity, and chemical actions, and even light were recognized as arising fundamentally from the electromagnetic force. Based on Maxwell's success, the search for a common mathematical description or unification of forces had begun. With the 20th century came the discovery of radioactivity, the probing of atoms, and the subsequent realization that more than just gravity and electromagnetism would be needed to explain this new world. Both a new dynamics, the laws of quantum mechanics, which superseded Newton's laws on atomic and subatomic distance scales, and new forces were needed. Because Newton's laws do not apply on the distance scales at which the new forces act, we shall not pursue the study of these forces further. Nevertheless, many theses, such as the quest for the fundamental constituents of matter and the fundamental forces of nature, carry over from classical mechanics, and it is interesting to survey briefly what has been found. Experiments probing atoms revealed that inside an atom there's a compact center, the nucleus, comprised of positively charged protons and neutral neutrons. Negatively charged electrons orbit the nucleus, held by the electric force from the protons. The natural question which arose is, what holds the nucleus together? Physicists realized that neither gravity nor electromagnetism held the compact nucleus together, but that a new force was at work. Aptly named the strong force, it overcomes the electric repulsion between protons and holds the nucleus together. Unlike gravity and electricity, the strong force does not extend to great distances. It has a limited range. The size of a nucleus, 10 to the minus 13 centimeters. Outside this range, the strong force has virtually no effect. If it did, we wouldn't be here. Matter would collapse into dense lumps of subatomic particles. Natural radioactivity could not be explained in all instances by any of the known forces, strong, electromagnetic, or gravitational. Another force was implicated in the decay of nuclei, the weak force. This force is intrinsically weaker than the strong force and has even more limited range, about 10 to the minus 16 centimeters, or 1/1000th the size of the nucleus. Because of its severely limited range, its most common manifestation of nuclei are feeble indeed, about 10 to the minus 6 times weaker than the strong force. Nevertheless, the weak force plays an essential role in the release of nuclear energy in stars, nuclear power plants, and in causing some stars to ultimately explode. The behavior of our four fundamental forces of nature, strong, electromagnetic, weak, and gravitational, is reasonably well understood, but nobody knows why there should be four of them. Albert Einstein spent the last 20 years of his life unsuccessfully searching for a way to unify two of the forces, gravity and electromagnetism. 20th century physics has become a story of attempting to explain all the complexities of physics as aspects of similar systems, a search for unification of the fundamental forces. The water clocks and inclined planes of Galileo have been replaced by increasingly larger, more energetic particle accelerators. Unified theories are emerging that bring together the weak electromagnetic forces, as well as more comprehensive theories that attempt to give a coherent account of how all these forces may have evolved from simpler laws in the infancy of the universe. The early universe may be the only experimental test for such theories. It may be the great ocean of truth that still lies undiscovered before us. That's the end of the chapter. It sums up very well three other forces beyond the gravitational force. Here's a table of the four fundamental forces in order of strength. Gravity is by far the weakest, followed by the weak force, the electromagnetic force, then the strong force. Electromagnetism and gravitation dominate, however, because of their far-reaching range. If you were to hold a magnet over a piece of iron metal and then move the magnet closer, eventually the iron metal will fly up and attach to the magnet. Think about that. The Earth's gravity is generated by its mass, which is 5.97219 times 10 to the 24th kilograms. When the iron metal flies up and attaches to the magnet, the electromagnetic force has overcome the force of gravity generated by a 5.97219 times 10 to the 24th kilogram sphere. That tells you something about how weak the gravitational force is. Gravity dominates the universe because of how much matter there is in the universe. Electromagnetism, when there are charged particles, dominates when there's charged particles. Most of the matter in the universe is neutrally charged. When it isn't, things tend to neutralize, which is what's happening with lightning. Henry Cavendish was a British natural philosopher and experimental and theoretical chemist and physicist. He's noted for his discovery of hydrogen. He was distinguished for his great accuracy and precision in his research into the composition of atmospheric air, the properties of different gases, the laws governing electrical attraction and repulsion, a mechanical theory of heat, and calculations of the density and hence the weight of the Earth. His experiment to weigh the Earth has become known as the Cavendish Experiment, and years later physicists were able to use his results to calculate the gravitational constant g. He performed the Cavendish Experiment in 1797 to 98. It was the first experiment to measure the force of gravity between masses in the laboratory and the first to yield accurate values for the gravitational constant. The gravitational constant does not appear explicitly in Cavendish's work. Instead, the result was originally expressed as the mass of the Earth. The experiment was devised sometime before 1783 by geologist John Mitchell. However, Mitchell died in 1793 without completing the work. After his death, the apparatus passed to Francis John Hyde Wollaston and then to Henry Cavendish, who rebuilt the apparatus but kept close to Mitchell's original plan. Cavendish carried out a series of measurements with the apparatus. The apparatus was a torsion balance made of a 6-foot wooden rod suspended from a wire with a 2-inch diameter 1.61 pound or 0.73 kilogram lead sphere attached to each end. Two 12-inch, 348 pound or 158 kilogram lead balls were located near the smaller balls about 9 inches away. They were held in place with a separate suspension system. The experiment measured the faint gravitational attraction between the small balls and the larger ones. The two large balls were positioned on alternate sides of the horizontal wooden arm of the balance. The mutual attraction to the small balls caused the arm to rotate, twisting the wire supporting the arm. The arm stopped rotating when it reached an angle where the twisting force of the wire balanced the combined gravitational force of attraction between the large and small lead spheres. By measuring the angle of the rod and knowing the twisting force or torque of the wire for a given angle, Cavendish determined the force between the pairs of masses. Since the gravitational force of the Earth on the small ball could be measured directly by weighing it, the ratio of the two forces allowed the density of the Earth to be calculated, using Newton's law of gravitation. The formulation of a gravitational constant did not become standard until long after Cavendish's time. One of the first references to G is in 1873, 75 years after Cavendish's work. Cavendish expressed his result in terms of the density of the Earth. He referred to his experiment in correspondence as weighing the world. Later, authors reformulated his results in modern terms. Cavendish's value for Earth's density, 5.448 grams per centimeter cubed, that gives a value of G equal to 6.74 times 10 to the minus 11th meters cubed over kilograms seconds squared, which differs by only 1% from the currently accepted value, 6.67428 times 10 to the minus 11 meters cubed over kilograms seconds squared. Some historians of science have argued that Cavendish did not measure the gravitational constant. Physicists, however, generally do credit Cavendish with the first measurement of the gravitational constant.